Good morning, students. I am Professor Arvind Mudodiha. Welcome you to the subject Design of Machine Elements 1. And today we will start with the module number 3. In that we have design of keys and couplings. So first we will study about the design of keys. To start with the design of keys, first let us understand what is key and what is its function. In general, a key is used to connect two pieces in such a way that there is no relative rotational moment between them. So we can say key is a piece of mild steel. Usually it is made of mild steel and it can be other material also, which is inserted between the shaft and head or both of the pulley to connect these together in order to prevent relative motion between them. It is always inserted parallel to the axis of the shaft. Keys are used as a temporary fastening and are subjected to considerable crushing and shearing stresses. So basically key is used to transmit the motion, or we can say it prevents the relative motion between the two parts, and key is always used as a temporary joint, and key is subjected to crushing and shearing stresses. If you consider example of keys can be used to connect shaft and gear and even shaft and pulleys. So therefore keys are subjected to shearing and torsional stresses. It is driven parallel to the axis of the shaft. To accommodate keys, axial grooves called keyways are cut on the outer surface of the shaft and on the inner surface of the bore of the mating parts. So this is all about the key. Next we will see the types of keys. In the types of keys we have first one sunk key, saddle key, tangent key, round key and spines. The sunk keys are provided half in the keyway of the shaft and half in the keyway of the hub or base of the pulley. The sunk keys are further classified as rectangular sunk key, square sunk key, parallel sunk key, gib head key, feather key and woodruff key. A rectangular sunk key, which is also known as taper sunk key. Taper sunk keys are rectangular or square cross section, uniform width with their bottom surface straight and upper surface tapered. It is sunk in the shaft to a depth of 1/2 its nominal thickness and the remaining portion fits into the keyway of the mating part. A taper sunk key can be used for heavy or medium duty as shown in the figure. The industrial practice is to use a square key with the sides equal to 1/4 of the shaft diameter and length at least 1.5 times the shaft diameter. That is, width of the key we can take 1/4 of the diameter of the shaft. Thickness of the key can be taken as T is equal to 2 times the width divided by 3, or we can take D by 6 as the thickness of the key, where D is the diameter of the shaft. The key has a taper of 1 in 100 on the top side only, and the bottom of the key will be flat. So this is about the rectangular sunk key. Next we look into square key. The difference between the rectangular sunk key and the square sunk key is that its width and thickness are equal. Okay, so we can take width W is equal to thickness of the key T is equal to D by 4. So it is the only difference between the rectangular and sunk key. Next we have parallel sunk key. The only thing we need to notice here in the parallel sunk key, it is a taperless key. Okay, the parallel sunk keys may be of rectangular or square section, uniform in width and thickness throughout. Okay, there is no taper portion in the parallel sunk key, and usually it is used where pulley, gear or other mating pieces is required to slide along the shaft. So in that case, the parallel sunk keys are useful. Next we have gib head key. This key is similar to square or rectangular key with the head projected from one face at the large end of the key. The key with gib head is withdrawn by hammering on a wedge-shaped piece which is inserted into the gap between head and end face of the mating part. So using gib head key, it is easy to remove the key from the assembly of shaft and gear or the shaft and pulley. The usual proportion of the gib head key are given here. You can see the width of the key is again D by 4, that is the diameter of the shaft. Thickness at the larger end can be taken as D by 6 of the diameter of the shaft. So this is about the gib head key. Next we have a feather key. A feather key is a parallel key which is fixed either to the shaft or to the head and which permits relative axial movement between them. A feather key is a sunk key of uniform width and thickness. While preventing relative motion, it permits sliding or axial movement. It may be of square or rectangular or dovetail cross section. The ends of the key and also the ends of the keyway in the shaft are rounded as shown in the figure. Sometimes it is secured to the shaft or hub by two or more set of screws. Here you can see set of screws or cap screws having countersunk heads. The special feature of the feather key is it transmits a turning moment and also permits axial movement. It is fastened either to the shaft or hub, the key being a sliding fit in the keyway of the moving piece. Next we have woodruff key. Here it is shown in the figure, the woodruff key, and here you can see the live picture of the woodruff keys. Here you can see. It is an easily adjustable key. It is a piece from a cylindrical disc having segmental cross section in front view as it is shown in the figure. A woodruff key is capable of tilting in a recess milled out in the shaft by a cutter having the same curvature as the disc from which key is made. This key is largely used in machine tool and automobile construction. In this, woodruff key has some advantages as well as some disadvantages. If you look into the advantages of the keys, it accommodates itself to any taper in the hub, and it is useful on tapering shaft ends. Its extra depth in the shaft prevents any tendency to turn over in its keyway. The major disadvantage of this key is that the depth of the keyway weakens the shaft, that is, it reduces the life of the shaft. and it cannot be used as a feather. Next we have saddle keys. In the saddle keys we have two types. One is a flat saddle key and another is a hollow saddle key. So in this figure you can see here we have a flat saddle key, and on the right side we have a hollow saddle key, and here you can see at the bottom it is a flat, and where in case of hollow saddle key at the bottom it is curved. Okay, so that makes the difference between the flat saddle key and the hollow saddle key. A flat saddle key is a tapered key which fits in a keyway in the hub and is flat on the shaft as shown in the figure. So it is a flat surface on the shaft. It is likely to slip round the shaft under the load. Therefore, it is used for comparatively light loads. Where in case of a hollow saddle key, it is a taper key which fits in a keyway in the hub, and the bottom of the key is shaped to fit the curved surface of the shaft. So as it was shown in the figure, the bottom of this hollow saddle key was curved to the shape of the shaft. Since hollow saddle keys hold on by friction, therefore these are suitable for light loads. It is usually used as a temporary fastening in fixing and setting eccentrics, cams, etc. Next we have tangent keys. Tangent keys are used in heavy duty equipment. Tangent keys are actually a pair. These pair of keys are placed right angles to each other and tangent to the surface of the shaft as shown in the figure. So here we have two tangent keys. Each key will withstand the torsion in one direction only. So this is about the tangent keys, and we have to remember that these keys are used in the large heavy duties. Next we have round keys or tapered pins, and here you can see in the figure it is shown the round keys. Okay, here you can see, and this is the tapered pins what we are seeing. Okay, the round keys are circular in cross section and fit into the holes. The round keys will be placed half portion hole in the shaft and the other half portion hole in the hub as shown in the figure. These types of shafts keys are usually prepared for the low power drives. The advantages of these keys are their keyway may be drilled and reamed after the mating parts have been assembled. Round keys are usually considered to be the most appropriate for low power drives, and sometimes tapered pin as shown in the figure is held in place of the friction between the pin and the reamed tapered holes. So what we have to remember is the round keys are used for low power drives, and which is the most appropriate for these kind of drives. Next we have the splines. The figure shows the spline key. Okay, here you can see capital D indicates the larger diameter of the spline, and small d indicates the smaller diameter, and B is the width of the spline, and here the proportional dimensions of the splines are given here. All about the mentioned keys are individual parts. The previously what we have discussed, it is all about the individual parts. They were individual keys. Now, when the keys are integral parts of the shaft or hub, that what we called as the spline shafts. These are used in the special applications like where we have to transmit the torque larger in portion than the size of the shaft. We can see there is these spline shafts in an automobile transmission, sliding gear transmission, etc. The thing to be noted here that using these splines we can transmit the more torque than the size of the shaft. These shafts usually have 4, 6, 10 or 16 splines. The splined shafts are relatively stronger than the shafts having a single keyway. Using these splined shafts, we can obtain axial moment as well as the positive drive of the shaft. Next, let us see the forces which are acting on the sunk key. So, when a key is used to transmitting torque from shaft to a rotor or hub, we can see that the key will be experiencing two types of the forces. One is a compressive stresses and other is a shearing and compressive stresses that we call it as a crushing stresses. This compressive stresses is due to the tight fitting straight key or in a tapered key driven in place, and this crushing stress is due to the torque transmitted by the shaft. So these are the two forces which will be acting on the keys. The distribution of the forces along the length of the key is not uniform because the forces are concentrated near the torque input end. The non-uniformity of distribution is caused by the twisting of the shaft within the hub. So in the design of keys, forces due to fit of the key are neglected and it is assumed that distribution of forces along the length of the key is uniform. Next we have a strength of the sunk key. The figure shows the force acting on a key for a clockwise torque being transmitted from a shaft to a hub as shown in the figure. And here you can see this is the thickness of the key, okay, and this is the length of the key, and this is the shaft what we have, and F is the tangential force which is acting on the key, and W is the width of the key. So let us take the torque transmitted by the shaft as a capital T, F as the tangential force which is acting on the circumference of the shaft, and B is the diameter of the shaft, length of the key as a L, and W is the width of the key, and small t can be taken as the thickness of the key, tau is the shear stress for the material of the key, and the sigma c e can be taken as the crushing stress for the material of the key. But due to the power transmission by the shaft, the key may be failed due to the shearing or crushing. Considering the shearing of the key, the tangential shearing force acting at the circumference of the shaft can be taken as F is equal to L into W into tau, where F is the area resisting shearing into shear stress. Therefore, it is L into W into tau, and the torque transmitted by the shaft can be written as capital T is equal to F into D by 2, or it can be taken as L into W into tau into D by 2, where area of resisting shearing is nothing but L into W, and shear stress is taken as a tau. So this area of resisting shearing is given by L into W, that is length of the key into W as the width of the key, and torque transmitted by the shaft is written as F into D by 2. So F is given in the above equation, that is L into W into tau into D by 2, where D is the diameter of the shaft. Considering crushing strength of the key, the tangential crushing force acting at the circumference of the shaft can be taken as F is equal to area resisting crushing into crushing stress, and area resisting crushing can be taken as L into T by 2 into crushing stress sigma C. Therefore, torque transmitted by the shaft can be written as T is equal to F into D by 2, where F can be written as L into T by 2 and crushing stress is written as a sigma C and into D by 2, where this parameter is nothing but the F, and this is D by 2. So torque is equal to, we can say, F into D by 2. We can find all these equations in the data handbook. As we further proceed to the solving problems on the keys, so during that I will tell exactly what is the equation number in the data handbook that can be referred. Now we can consider the key is equally strong in shearing and crushing. Therefore, we can equate equation number 1 equal to equation number 2. Equation number 1 we have L into W into tau into D by 2, and equation number 2 we have L into T by 2 into sigma C into D by 2. After equating these two equations, resolving this equation, we get D by 2 will be cancelled and length will be cancelled. So we get W and we'll bring this T on this side, so it is W by T which is equal to, we have 1 by 2 here into sigma C, and we'll bring the tau on this side, so it will go to the denominator. So finally we will get W by T is equal to sigma C divided by 2 tau. The permissible crushing stress for usual key material is at least twice the permissible shearing stress. Therefore, from the above equation we have W is equal to T. In other words, a square key is equally strong in shearing and crushing. So that is the advantage of using the square key, which will give us the equal strength in shearing and crushing. In order to find the length of the key to transmit full power of the shaft, the shearing strength of the key is equal to the torsional shear strength of the shaft. So from the previous discussion, we know that the shearing strength of the key can be written as T is equal to L into W into tau into D by 2, and the torsional shear strength of the shaft can be written as T is equal to pi by 16 into D cube into tau 1, where tau 1 is the shear stress for the shaft material. So from these two equations, that is, this is equation number 4 and this is equation number 5. From equation number 4 and 5, equating both the equations, that is W into L into tau into D by 2 and pi by 16 into D cube into tau 1. For some key width, we can take W is equal to D by 4, and the key material is same as that of the shaft, that is tau is equal to tau 1. We can take length of the key as L is equal to 1.571 D. After solving this equation, we are going to get this L is equal to 1.571 times the diameter. So by doing this, we found the length of the key, what is the suitable length of the key, and also we found what is the shearing strength and the crushing strength of the key. By using all these equations, we can find the dimensions of the key and suitability of the key for the given tau to be transmitted. So this is all about the introduction of the key. In the next class, we are going to study the few problems on the keys and what are the equations which are used in the data handbook to solve the quiz. So we will look into the problems in the next class. If you have any queries, feel free to ask your queries. Thank you.